In this final project, we developed a panorama image 6 degree of freedom warping using an icosphere control method. The authors for this project are Nathan Riopelle and Philip Yao. To begin, let's talk about virtual reality. There's been a huge popularity increase in virtual reality nowadays. The applications of VR extends from gaming to education to generally viewing 360-degree panorama images and videos. However, there is a problem with the latter utilization. If a user shifts in a direction, how will the panorama image warp itself such that the user believes they have also shifted in the virtual world? For example, if you considered a 2D image, the 2D image can be warped such that it appears that the 2D image was taken from a different angle. Similarly, we would like the panorama image to warp such that it appears that the user is at a different location. Previous work has tackled this problem. It has mainly fallen into two areas: free viewpoint video and video stabilization fields. Kanada et al. Used a dome of cameras to reconstruct scenes that is then used for viewpoint synthesis. The scene that were reconstructed was very high definition, but required very high-tech equipment and many cameras, which is very expensive. Liu et al. Constructed a novel warping algorithm for video to make the video appear that it was taken from a different viewpoint. His work fell into video stabilization, but also tackled our problem. Charasia et al. Developed a new image-based rendering for free viewpoint navigation, also tackling the problem that we are trying to solve. However, the work that we are basing ourselves off of is 6 degree of freedom VR videos with a single 360-degree camera, a paper by Jingwei Huang et al. They developed a novel warping algorithm to synthesize virtual viewpoints. Our project re-implements their research.
Next, I want to present to you the approach that we use to generate our novel panorama images using the warping process. This approach was divided into two parts: an offline segment and an online segment. During the offline segment, which we performed ahead of time, we used the structure from motion algorithm to take a sequence of panorama images, all constructed within the same scene at different viewpoints, to construct a 3D point cloud of the scene. We then defined an icosphere control mesh at the center of the viewpoint of the panorama image that we wanted to warp, and defined a conjugate direction field on the surface of the icosphere that we used to parameterize our warping. During the real-time portion, we took our 3D point cloud and projected it onto the surface of the sphere. We also took our point cloud and then shifted it based on the translations of our headset, and we projected the shifted points onto the control sphere as well. These are the points Q and QM prime for the non-shifted and shifted points respectively. We then optimized an energy function given by the two equations below to retrieve the optimal conjugate direction field parameters that were used to parameterize how much each point moves over the surface of the sphere during the warp. The results of our algorithm are shown in this GIF. Unfortunately, our algorithm ran very slow, so we weren't able to get the true real-time VR demo that we wanted, but we're still able to generate lots of small images at small translation, compile them into this short GIF, which you can see we're moving along a single axis back and forth. You can see how we're getting closer and farther away from some buildings as we're translating through the scene. We were also able to render this GIF as a 360 video shown in this image, where we're actually rotating. So that's one of the three degrees where we're rotating our head while the translation is also going on. So you can see that while we're looking around the scene, we're also going back and forth. So it's like we're moving our head back and forth within the scene. And this is what it would look like if you were viewing it in VR. In future work, we would obviously like to improve our runtime performance so that we get the real-time VR demo. We hope to do this by optimizing vector code and also moving the code to an OpenGL compute shader so we can run it on a GPU. And we're also considering using different meshes besides triangles for a control mesh, possibly rectangles or pentagons. Thank you. I hope you enjoyed this presentation.